Welcome to today's paper reading. Today's paper is titled ClashEval, Quantifying the Tug-of-War Between an LLM's Internal Prior and External Evidence. This paper, titled ClashEval, Quantifying the Tug-of-War Between an LLM's Internal Prior and External Evidence, was authored by Kevin Wu, Eric Wu, and James Zhou from Stanford University. It is currently under review as a preprint. Retrieval augmented generation, RAG, is employed to reduce hallucinations and supply current knowledge to large language models, LLMs. However, the imprecision of document retrieval can lead to erroneous or harmful content. This study investigates how LLMs manage retrieved information, particularly when it is incorrect. The research questions focus on whether models can recognize and ignore incorrect data, and whether they use retrieved information to correct initial errors. To address these questions, a data set of over 1,200 questions across 6 domains was curated, with precise perturbations applied to the answers. The study found that LLMs frequently adopt incorrect retrieved content, overriding their own correct knowledge in over 60% of cases. The likelihood of adopting incorrect content decreases as the content becomes more unrealistic. Additionally, models with lower confidence in their initial responses are more likely to adopt retrieved information. This research highlights the challenge of correctly discerning and handling retrieved content, and introduces the ClashEval dataset for future benchmarking. Large language models, LLMs, are known for their propensity to produce hallucinations and incorrect answers. They are limited by the knowledge contained in their training corpus, which restricts their ability to answer queries about recent events or publicly restricted information. To address these issues, the Retrieval Augmented Generation (RAG) framework is commonly used. RAG enhances model accuracy by providing relevant retrieved content in the LLM prompt. This framework is employed by commercial LLMs like ChatGPT and Gemini, which use search engines to retrieve information. However, this practice raises concerns about the quality of retrieved documents, as they may contain incorrect or harmful information. Our study introduces ClashEval, a benchmark dataset that tests the LLM's ability to arbitrate between its own parametric knowledge and contextual information. We also benchmark several top-performing LLMs and analyze their context preference rates. Figure 1 illustrates the process of generating modified documents for each dataset. A question is first posed to the LLM with and without a reference document containing information relevant to the query. The document is then perturbed to contain modified information and provided as context to the LLM. The figure then observes whether the LLM prefers the modified information or its own prior answer. The issue of hallucination in large language models, LLMs, has been extensively studied across various contexts and models. Research has shown that retrieval augmented generation (RAG) systems can effectively reduce hallucinations. However, RAG can still mislead LLMs when faced with complex or misleading search results. In terms of evaluation, previous works have developed automated frameworks to assess RAG systems, often using models like GPT 3.5 to evaluate factors such as faithfulness and relevance. Additionally, metrics like noise robustness and counterfactual robustness have been proposed. While some studies have used log probabilities to gauge model confidence, there is a lack of systematic exploration linking this confidence to the preference for RAG-provided information. Furthermore, efforts have been made to address model adherence to incorrect context, such as pre-training on substituted facts or ensembling answers across multiple documents. In this study, the QA instance is defined as X equals QC, where Q represents the query and C is the context provided to answer the query. The model's prior response is denoted as RQ, which is the model's answer based solely on its parametric knowledge. The contextual response RQC is the model's answer when its response is conditioned on the provided context. To evaluate the model's performance, 3 metrics are defined: accuracy, which measures the probability that the model responds correctly given that either the context is right or the prior is right; prior bias, which measures the probability that the model uses its prior while the context is correct; and context bias, which measures the probability that the model uses the context while the prior is correct. In this section, we discuss the performance of various models and conflict resolution between prior and context information. Claude Opus stands out with the highest accuracy at 74.3%, while GPT-4o and Llama 3 have accuracies of 61.5% and 50% respectively. Regarding context bias, Claude Opus shows the least bias at 15.7%, compared to 30.4% for GPT-4o and 26.4% for Llama 3. Interestingly, all models exhibit similar levels of prior bias, with Claude Opus, GPT-4o, and Llama 3 all at 2.1%. These results highlight the varying degrees of reliance on context versus prior knowledge across different models. Table 1 provides an overview of the datasets used in the study, detailing the number of questions, the number of perturbations applied to each question, and an example question from each domain. The table highlights that the study covers 6 different subject domains, with a total of 1,294 questions. Each question undergoes 10 perturbations, which are crucial for evaluating the model's response to modified information. This setup allows for a comprehensive analysis of the model's ability to arbitrate between its prior knowledge and the contextual information provided. Figure 2 showcases examples from 3 datasets: drug dosages, sports records, and news, illustrating how large language models, LLMs, respond differently to various types of context modifications. The responses are color-coded. Red indicates incorrect answers, while green indicates correct answers. This visualization helps in understanding the performance and reliability of LLMs across different contexts and datasets. Table 2 presents the behavior of various models when faced with a conflict between prior knowledge and context information. The table highlights instances where models exhibit prior bias by selecting their prior knowledge even when the context is correct, and context bias by relying on the context when the prior is correct. Additionally, it reports cases where neither the prior nor the context answer is utilized in the model's response. Figure 3 illustrates the inverse relationship between the context preference rate on the y-axis and the amount of deviation from the prior on the x-axis. The plots show absolute deviations from reference information, with specific treatments for numerical datasets, up to 2 log-fold changes with the trend line, years, absolute number of years, and categorical datasets, for modification categories. This visualization helps in understanding how models prefer context based on the degree of modification from the prior. Table 3 evaluates the performance of models that provide token probabilities under 3 conditions: no correction, token probability correction, and calibrated token probability correction. The results show that accuracy improves with both types of corrections, with the calibrated token probability correction achieving the highest accuracy. However, this method also introduces more prior bias. Despite the increase in prior bias, the calibrated token probability correction method outperforms a baseline of randomly replacing the final response with its prior. Figure 4 illustrates the inverse relationship between the context preference rate and the model's prior response probability. The context preference rate is the proportion of responses that align with the information provided in the context. The prior response probability is calculated from the average log probability of the response tokens without context. The plot groups prior probabilities into 10 bins and shows the best fit trend line and slope, highlighting the effect of model confidence on context preference across different models. The ClashEval benchmark reveals that even advanced LLMs like GPT-4o show a significant context bias, overriding correct prior knowledge over 60% of the time when faced with incorrect information. This bias is influenced by the degree of deviation from truth in the retrieved content. Each LLM has a unique prior distribution over truthfulness across domains, affecting how they respond to perturbations. For example, Claude Opus is less prone to incorrect contextual information compared to GPT-4o. Additionally, LLMs selectively defer to external evidence when uncertain, but calibration levels vary. However, the study has limitations including restricted domain coverage, fact-based question generation, and an enriched rate of contextual errors in the dataset. These insights highlight the need for further research to enhance the robustness and calibration of retrieval augmented AI systems. Thank you for watching.